How's it going, guys? So today I want to be able to inform you guys about ionizing radiation. What is ionizing radiation? Ionizing radiation contains sufficient amount of energy to deposit energy into matter and interact with matter. So a lot of the times when people think about radiation, they automatically freak out because they don't really know the backslash behind it, I guess. So today I'm going to try to break it down into basic principles and just try to explain it to you guys and inform you guys about ionizing radiation. So we'll start with the term itself, ionizing radiation. So what does ionizing mean? So essentially, ionizing is essentially it's able to the radiation is able to remove orbital electrons from matter, from atoms. So what are orbital electrons? Orbital electrons are just electrons that orbit the outermost shell of most atoms. So in essence, there's many different types of ionizing radiation that can do this, right? So we'll first start off with what an alpha particle is. So alpha particles are relatively big. They're basically helium nuclei with plus 2 charge. So if you guys want to think about this, you can think about this as opposed to the other types of radiation that I'll explain. You just think about it as something that's relatively big. Okay, so then you have alpha radiation, you have beta radiation, beta plus and beta minus. It's essentially an electron. You can think of it as an electron. It's relatively small, right? So you have alpha, beta, and you have gamma. Gammas are photons. They're like light. So basically, they don't have no charge and they can travel, hundreds of feet. And then you have alpha, beta, gamma, and then you have protons, which are basically a positive charge. I'm sure we all know what protons are. Neutrons that have no charge. Those have to essentially interact first, and then that's how they deposit energy into matter. So going over those basic types of radiation, to put things into perspective, I guess alpha particles, like I said, they're relatively big, and they're not really an external radiological hazard. They're an internal radiological hazard, meaning if you ingest this type of radionuclide that emits this type of radiation, then it'll essentially be very damaging. As far as betas, it's the same thing. They can only penetrate a certain depth to your skin, to the dermis. Gammas, they'll go right through you, but they don't have much as damaging properties as the alpha particles. So I guess you can kind of put that into perspective. Anything with charges, like I said, the alpha particle is densely ionizing, meaning it'll cause a lot of ionizations per micrometer within the cell. Betas, they're almost as bad, but not entirely as bad. Sparsely ionizing radiation, like photons, they don't really deposit that much energy into matter. So it's not really that crazy as far as alpha particles, but you kind of see where I'm going with this in a sense. So a lot of the times people are confused about radiation. Sometimes they think it's all contamination, or they think that they're gonna die. But in reality, I think, like as I mentioned earlier in the video, that a lot of people don't have the backslash of the knowledge to put things into perspective, so they're afraid of it, right? So I'm here today, I guess, to inform you guys that radiation isn't all that bad. I mean, it's just like anything else. You get a large amount. You do, like let's just bring in alcohol, for example. If you drink in moderation, it's fine. But if you start drinking a lot and doing a lot, then it can become very damaging. It's kind of like the same concept with radiation. You take on a lot of dose, a lot of time, and it's going to be damaging. But if it's small amounts, you're going to be fine. In terms of radioactivity, it's all around us, right? We're all breathing right now as I'm speaking. As you guys are watching, you guys are breathing natural radon, which is it's a radioactive gas. It's going through your lungs. It's ionizing your cells. Your body is going through a bunch of ionizing, as just from living. The chemicals we breathe, the stuff we eat, it's affecting us in the same manner. It's just that when you're exposed to ionizing radiation, it's increasing that frequency of ionizations per se. So as I mentioned, radiation is all around us. There's natural radon, natural gas steaming from the Earth's crust, and we're living. The average person picks up around 320 to 620 milligrams per year, which is it's a mediocre dose in a sense, but that's just from living, right? So, as I mentioned, a lot of people are scared of radiation. They're extremely scared. But as I mentioned, it's as long as you have, as long as you don't take on such a big dose, you'll be fine. So as I guess I'll dig in deeper and talk a little bit about radioactivity. So if you guys imagine the periodic table, you have all these elements. Within all these elements, if you look in a little bit deeper, you have a bunch of isotopes. Isotopes can have the same Z, different A, meaning they have the same number of protons, but a different number of combination of protons and neutrons. So there's a certain ratio, I believe there's a 2-to-1 ratio, where you have all these radioactive isotopes, radioisotopes. So what they're trying to do is they're decaying in the form of the types of radiation that I just explained. They're decaying in that manner so that they can become more stable, so they can reach a more stable state. As they're doing so, they're releasing energy. That energy can interact. It interacts with matter, but it interacts with, our primary concern as humans in health physics, we're primarily concerned with our body and how that radiation is interacting with our body. So what's happening is you create ionizations within the cell. Within that cell, it's mostly composed of water, right? So you can have all these free radicals. These free radicals they essentially can recombine, or they can adjust and reform into like hydrogen peroxide, which is extremely damaging to the cell. That's what we don't really want. We don't want too much of that happening because that can create cancer in the long run. But what we usually typically go by and what the studies show is there's a linear no threshold model, meaning that as you pick up dose, you're increasing your risk of developing fatal cancer. That's the most hypothetical, and it's the most conservative route as far as, like the NRC, DOE, we all INCRP, we all use this type of model so that we can estimate what the yearly dose of people would be and keep doses safe and all that good stuff. But if there's been studies that actually show that there's a dip in that, saying that, okay, well, as you take on a little bit of dose, it's actually beneficial for the body, and then it goes up. That's called radiation hormesis, and there's a lot of studies out there. But then again, that if we were to change the context of the model, then we'd have to change everything else, and maybe we wouldn't have such a conservative approach as we do now. But yeah, that's a little bit of a backslash on, I guess, ionizing radiation. So I guess don't be scared of it. Just think about it as it's all around us. It's natural. Not all radioactive elements are man-made. Some of them are man-made. Most of them are natural. But it's all around us. So there's nothing to be scared of. Just think about it as like drinking. The more that you drink, or the more that you do too much of anything, it can become damaging. And it's the same concept with ionizing radiation.